So now, in the previous lectures, we discussed the relationship between the force and the corresponding work done on the system or the energy of the system. And we found a special class of force or forces which we call conservative forces, where one can actually define the path integral in terms of a scalar function, now termed as potential energy. And then we also saw that for conservative forces, the sum total of the kinetic energy and potential energy at any given instant is a constant, and that then gives us the law of conservation of mechanical energy. Okay, so continuing from there, now what I can say is, so for a system in general, I can say that for all the forces that are acting on that system, we can say that a general system is under the influence of conservative forces, as well as there could be some non-conservative forces. So a general system can be the force applied on a general system can be written like this, and then what it gives us is, now I can write down my path integral, which was f dot dr as integral of, or the path integral of conservative forces plus the path integral over the same path in case of the non-conservative forces applied on the same system. We know that for conservative forces, this path integral can be simply written as the change in potential energy, right? And for non-conservative forces, we don't know. So we basically have to calculate the path integral as it is. Okay. On the right hand side, what we have is, we also wrote this down as in terms of the work done as, well, here we have 2 points over which we are looking at the influence of the force. So we have this equation. And now what I can do is, I can slightly modify this, rearrange the terms. So integral, path integral of the non-conservative force is equal to, well, which is then the total energy, total mechanical energy, kinetic plus potential at point B minus the total energy at A. So of course, what we have seen is, instead of this energy being constant now, this energy is different at 2 different points, and that is purely because now there are non-conservative forces. Okay? So this then becomes our important result. And what it states is, so this I can still write as, or I write this as work done in going from A to B by non-conservative forces, right? Because this is how we define this path integral. So in the statement form, then it becomes work done by a non-conservative force is equal to, C, is equal to change in total mechanical energy of the system. So this is an important result that we have to keep in mind, that if the system is under application of conservative forces, total energy will remain constant. If there are non-conservative forces, then no, total energy is not a constant, and there will be a change in total energy as the system evolves from one instant in time to another, or from one point to another. Okay. Now the thing is, we are not going to talk about this non-conservative forces any further, primarily because there is not much that we can now talk about it. Other than, if you have a non-conservative force, then to find the work done by it, all you have to do is calculate this path integral. There is no further simplification, right? So we'll leave this here and come back to our conservative force. Okay, so now let me write down conservative forces and the potential energy function which we define as U of R, right? So what are the relation again? So let's start with our basic or our fundamental relation. We wrote down that in case of conservative force, now F is basically conservative force. F dot dr was the change in potential energy. We wrote down it this way. Okay. And of course, we had a different sign convention there, but that's okay. That is, let's take that here. So I'll write it as, so that there is no confusion. So this was UA minus UB in going from A to B, or I could have written down this minus UB minus UA, and I'll write them as delta of U. Right? So now this is the same sign convention or the same convention as we followed for kinetic energy. Okay, so this is my starting equation. Now let's say in one dimension, right? So for sources which are only, let's say, one dimensional problems, so basically what it means is we don't have to worry about the effector because we know that there's only one dimension associated with it. So in that case, I can simply write it down as f of, let's say, r, where r is the only coordinate, and then dr, the integral is only over this, and of course this will be minus delta of u, which is then also a function of, could be a function of r. Right? Okay, in general a function of r. If this is the case, then now this is a very simple equation, which what I can do is I can solve for fr by simply differentiating on both sides. So I can get f of r is equal to minus d of u over du. The standard procedure. And then this is the way we can find out the force if the potential associated with it is known, right? But when this potential will be known only in case of conservative force, right? So we should not look at, if we know that the forces governing the system are non-conservative, then we actually should not look for this kind of potential energy function, right? It will not make much sense. Anyway, so if this is the case, then this is what we get, and we can also write down this result as force acting on a system. Again, force meaning conservative force acting on the system is equal to negative spatial meaning in space coordinate, spatial rate of change of potential energy function u of r associated with that force. Right? So du over dr, we have seen that this is also termed sometimes as the slope of the function. So this is also the slope, right? So force is basically slope of the potential energy function. But this is true as a slope or as this equation only in case of a unidimensional problem, right? In general, for in 3 dimensions, for 3-dimensional problem, what we can do is we can write now f as a vector, which in general depends on r vector, as very analogous to this one, negative of u of r, where now this term del, this is a del operator, right? So this is a, well, first of all it's called the del operator. It's a vector operator. It's not a vector quantity in the sense that it's not the quantity in the sense of force or velocity or acceleration. It's an operator, so it has to act on some physical quantity. Nevertheless, this is a vector function, this is a vector operator, right? And the force is then equal to del of u of r, right, in 3 dimensions. The del operator is then defined as, so what is the value of this del operator? Of course, it is related to the differential in space. So it's defined as del over del x I cap plus del over del y j cap plus del over del z k cap. So this is the definition of the del operator, right? And these del over del x, del over del y, del over del z are nothing but partial differentials in along x coordinate, y coordinate and z coordinate. So instead of a differentiation along the coordinate r, because this was the only coordinate, now in 3 dimensions, this differential is replaced by a vector operator in 3 dimensions I, j and k. So again in the Cartesian coordinate system, where each differential is done in x coordinate. It's a partial differentiation. What it means is, when the differentiation is happening with respect to x coordinate, we don't consider changes in y or z coordinate. So consider changes related to y and z coordinate. Similarly, del over del y is then differentiation with respect to y coordinate, considering there are no changes with respect to x and z coordinate, and similarly here. So these are called partial differentials. Partial differentiation. Okay. So this is the definition of this del operator, and that's how it's defined. And what we can again see from here is, force is a vector quantity, u of r is a scalar quantity. We already defined that it is equivalent to a scalar potential. So it's a scalar quantity. So of course a vector quantity cannot be equal to a scalar quantity. However, a scalar multiplied by a vector, simple algebraic multiplication, gives us a vector quantity, where del, which is the operator, is the vector quantity. Now, another important thing that we have to note down is, or maybe we will note it down after one more step. And what is so what we do is, let's write down this. So since we have written down this in component form, we can again write down this vector also in component form. So I can write down fx I cap plus fy j cap plus fz k cap is equal to del over del x I cap plus del over del y j cap plus del over del z k cap u of r, right? And now, as we know from vectors, that if two vectors are equal, then they have to be equal. Their components also have to be equal. So fx has to be equal to x component of this vector, fy y component of this vector, and fz z component of this vector. What that gives me is the components of force. So given the potential energy function for a conservative force, I can find out the components by simply taking partial derivatives of the potential energy function along the 3 coordinate directions. Okay. So then these are the partial differentials. And now here I should mention that standalone, left as it is, this vector has no meaning. Right? So in the sense that, for example, force vector has a meaning. Whatever it points to a direction, it points to a location. The del vector as such does not have any meaning, in the sense that we don't know what del over del x is. Del over del x is partial derivative of something, so that something has to be known, and that, so if only when it's operated on a scalar quantity, it gains a meaning. And in this case, when you write it down like this, del u, this is termed as gradient of u. So effectively, it basically gives slope of u in all 3 different directions, right? So it's a gradient of u, which could be a function of r, right? However, left alone, del has no physical meaning as such. It's just a mathematical operator. Okay. Anyway, so this is the case And what now I do is I digress slightly. Yeah, let me remove all this.